Oh my god, guys. I think I forgot to turn off my lights. Wow, third time this week. Your electricity bill's gonna cry. Only if there was a way I could turn it off from here. You can actually do it. Huh? How? Let's see.
When you press a button on your phone, it sends a unique pair of tones. That way you can control your lights from anywhere. Simple.
Oh,
The DTMF identifies the key and acts on it. Simple and smart.
Hello everyone, welcome to our presentation on DTMF, that's Dual Tone Multi-Frequency Signaling. Hi, I'm Lippy and let's get started. Have you ever pressed a number on a phone keypad and heard that little beep? Well, that beep isn't random. It's special tone that carries your button press as a code. In this talk, we'll explore how DTMF works, how we simulated it in MATLAB, and how we built an Arduino setup to decode it. So, what exactly is DTMF? It's a language your phone speaks when you press a number. Each key you tap creates two unique sound frequencies, one low and one high. Together, they form a signal that tells the system, hey, someone just pressed 5. It's like a secret melody your phone sings every time you dial.
So the basic idea behind DTMF is actually really interesting. Every time you press a button on a keypad, it plays two sounds at once, one low frequency and one high frequency. These two mix together to form that unique tone you hear. It's not random either. Every button has its own special combination, so no two buttons sound exactly the same. That's what makes it so easy for all systems to tell them apart. Even if there is noise or static in the line, it still works because those two frequencies are always distinct. Here's how these combinations are set up. Think of this like a grid. The middle column shows the low frequencies and the right one shows the high ones. When you press, for example, the number 5, it picks one from each column, 770 Hz from the low frequency column and 1336 from the high frequency one, and plays both together. It's actually super smart because none of these frequencies are multiples of each other. That means they don't blend or create harmonics. So when we decode them later, we can instantly recognize the two main peaks and figure out exactly which key was pressed. That's why DTMF signals still sound clear even over noisy phone lines. Let's now look at how this was executed using MATLAB.
Alright everyone, now let's look at how we actually generate a DTMF signal using MATLAB. This code lets us create the same tones that your phone makes when you press a button. First, we clean up the workspace. This just clears the command window, removes all variable and closes any open figures, so we start fresh. Next, we define our DTMF frequencies. These are the official standard DTMF frequencies, the low group and the high group. Every key on the keypad is made by combining one from each group. Then, we define the keypad layout. This matrix tells MATLAB where each key sits. So, when we type a number, it can find the row and column to pick the right frequencies. Now for the fun part, the user input. Here, MATLAB asks us to enter a key. Say, I type 5. If you type something invalid, MATLAB will simply say, invalid key entered. Next, MATLAB finds the row and column of that key. Once MATLAB knows the row and column, it automatically picks the correct low and high frequencies for that specific button. For example, for key 5, row 2, 770 Hz, and for column 2, it's 1336 Hz. So the DTMF tone for key 5 will be made for those two frequencies combined. Now we set the sampling frequency and duration. Fs is 8000 Hz, meaning 8000 samples per second. That's standard for audio. T defines the time range. Here it's 0.5 seconds, so each tone lasts about 0.5 of a second. Then we generate a DTMF tone. This sign creates two sine waves, one for low frequency and another for high frequency, and adds them together. That's exactly what happens inside your phone when you press a button. And now for the best part, play the sound. So when I run this, MATLAB will actually play the DTMF tone to the speakers. You can try different keys. Each sound is slightly different because of its unique frequency pair. Then we plot the waveform and frequency spectrum. This first plot shows how sound wave looks in the time domain. Those ripples you see are the combined sine waves. And the second plot shows the frequency domain. This one shows two clear peaks, one at low frequency and another at high frequency. And those two peaks together represents the key that was pressed. So, for example, key 5 will show peaks around 770 Hz and 1336 Hz. And that's it. With just few lines of MATLAB code, we've created how your phone generates DTMF tones. It's a perfect way to understand how two simple frequencies can carry digital information through sound. So, the next time you press a button and hear that beep, remember, MATLAB can make that beep too. Pretty cool, right?
Once we've generated those tones in MATLAB, the next step is figuring out what they mean, basically decoding them, and this is where FFT or fast Fourier transform comes in. You can think of FFT like switching from listening to a sound to seeing it. It converts the signal from the time domain to the frequency domain so you can visualize which frequencies are in there. When we plot the FFT of a DTMF tone, two big spikes appear, one for the low tone and one for the high tone. The program just picks those two frequencies and checks the matrix to know which key was pressed. It's a really neat way to turn sound into data. We'll now look at how this is executed with the help of an Arduino circuit.
Let's have a look at a project simulation and understand how it works in real time. We have built a DTMF prototype model. This isn't a complete DTMF decoder like the ones used in telecommunication systems, but it's a simplified version that follows the same decoding principle. Instead of decoding tone signals from a phone, we are giving manual binary inputs using switches, and our Arduino Uno interprets those inputs and controls the output devices accordingly. It's simple, smart, and a fun way to understand how digital communications can control the real world devices. Now, let's go through the components used in our circuit setup. First, we have the Arduino Uno, which acts as the microcontroller, basically the brain of our project. It reads the input signals, processes them, and gives the output decisions. Next, we have used 4 push-button switches connected to pin number 2, 3, 4, and 5 of the Arduino. Each switch represents a single binary bit. Pressing a switch gives logic 1 and releasing it gives logic 0. Together these 4 switches form a 4-bit binary code that the Arduino reads. On the output side, a bulb is connected to pin number 8 and an LED is connected to pin number 9. Here the bulb represents the light and the LED acts as a fan or any other electronic device. It is just basic as an indicator. The whole circuit is powered by the 5 volts which is provided by the Arduino itself. So this is our setup, compact, clear, and ready for action. Now let's move to the working demonstration. This is where all the fun begins. Each combination of switch presses forms a binary code which the Arduino reads and converts into a decimal number. That number corresponds to a particular command, just like how a real life DTMF decoder translates the tones into numbers and actions. Let's test it out. So firstly we will start the simulation. Now when we press the switch 1, our binary code is 0, 0, 0 and 1, which is equal to decimal 1. So the Arduino identifies the command and toggles the bulb on. Now if we press it again, it turns off. So basically toggle means if the bulb was on earlier, it will turn off. And if it was off earlier, it will turn on by pressing 1. Next, if we press the switch 2, this gives the binary as 0, 0, 1, 0, which is equal to decimal 2, which toggles the LED on. So, and if you press it again, so the LED turns off. This means again the same thing by pressing the decimal 2. Now, if you press switch 1 and switch 2 together, we get 0, 0, 1, 1 or decimal 3, and this turns both the bulb and the LED on together. Finally, if we press the switch number 3 and switch number 1 together, so this gives us 0, 1, 0, 1 or decimal 5, which acts as a reset, turning both the LED and the bulb off at once. So our simple control logic is for decimal 1 we toggle the bulb, for decimal 2 we toggle the LED, for decimal 3 we turn on both the LED and the bulb, and for decimal 5 we turn off both, that is LED and the switch bulb will turn off. Pretty cool, right? It's like giving binary commands to the Arduino and it instantly obeys. One press, one action. Feels almost futuristic. Let us also understand the code logic behind all this. The Arduino continuously reads the digital inputs from pin number 2 to pin number 5 and stores them as zeros and ones. It then combines these bits into a single value. That value acts as a unique command number. Inside the code, we have used a switch case structure so that when the input value is 1, the bulb toggles. When it's 2, my LED toggles. Instead of LED, we can also connect any other device, which can be a fan also. Then when it's 3, both my LED and my bulb will turn on. And when it's 5, both will turn off. We have also added a small delay to prevent the multiple detections if the button is pressed roughly. That's called as debouncing. So overall the code is compact, clear and very beginner friendly. And that wraps up our DTMF prototype demonstrations. Even though we have not used actual tone decoding here, the working principle is exactly the same. Inputs are decoded, identified and used to control the outputs. This project helps us to understand how DTMF decoding, binary logic and microcontroller programming come together to build real-world automation systems. Plus, it's quite satisfying to see the bulb and LED responding instantly. It's like the Arduino saying command received. That's it.
Now that we've looked at DTMF through the perspective of an Arduino circuit, let's talk about how reliable it actually is. Even if you add a bit of noise or distortion, those two main peaks still show up clearly in the FFT. In our MATLAB test, the system detected every single tone correctly with 100% accuracy. This technology was built back in the 1960s. The fact that it still works so well today just shows how well designed it was. It's simple but rock solid. Even though it's old, DTMF is still used everywhere. All programs having instructions like press 1 for this or press 2 for that all use DTMF. It's also used in remote control setups. It's like sending tones over radio to activate relays or control small robots. You can even use it for basic home automation, turning lights on and off through a call. All this makes it super practical whenever you need low-cost, reliable control through audio. And from a learning point of view, DTMF is such a perfect example of applied signal processing. It shows you how two simple sine waves can carry digital information, how FFT helps you extract it, and how you can use logic to convert that into actual control signals. It's one of those projects where theory meets real life. You get to see math, code, and electronics all working together.
And that, my friends, brings us to the end of Journey into DTMF. We explored how those simple tones carry powerful meaning, how every pair of frequency represents a unique key. From generating signals in MATLAB to bringing them into life with our Arduino setup, we turn sound into action. What makes DTMF so amazing is its simplicity. It doesn't need fancy data lines or complex tech, just the power of sound. So, the next time your phone beeps, remember that tiny tone is actually talking. Every beep carries an information, every signal tells a story. Thank you guys for tuning in. We hope you enjoyed learning about DTMF as much as we enjoyed building it. Thank you.